He's recording us.
You were recording without my consent.
No.
What is okay? So for this engineering practice project, students are to create using Connects. They're meant to create an earthquake-resistant building. We are on trial 3 right now. Students are finding out that the more rigid the structure, the longer it takes for the building to stop moving on our earthquake table. So let's go over to our earthquake table. Where's the earthquake table? Okay. Here's our earthquake table. What we do with it, we attach the building to these 4 pegs, and then we cause the building to tilt on this table. So this table is creating waves, and the building should be flexible enough, or should have some sort of system or mechanic that allows it to cancel out these waves by creating its own waves and causing a disturbance in the lateral waves from the earthquake. So in a minute here, we'll get a building onto the earthquake table and we'll see how it goes. Like I said, they started off with very rigid structures. So here's an example. One of the first buildings that we made had
it's like supported.
Yeah, cross beams. Had cross beams attached to each piece. So they would have square, 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 and they'd have cross beams all the way down it. And because it was rigid, it would go back and forth. Now they were tested on when does the building stop shaking. So if it was rigid, the building would shake for as long as the table would shake. But they noticed that when they made a flexible building, the flexible building would bend and create a wave to act as interference to the earthquake wave. So we'll see what that looks like. If their earthquake rocked their building, oh, this kind of got erased. If their building stopped moving in less than 3 seconds, they got an A. If their building went more than 3 seconds, below 6 seconds, B. If their building kept moving from 6 to 15 seconds, C. D is 15 to 30 seconds, and F is longer than 30 seconds. Okay. So here one of our students who got an A. So Renzo, explain what you did with your building to get you an A.
Well, we basically started with a long base for flexibility.
Okay.
In the middle, we widened out the middle, so it would have an equal distribution of weight. And on top, we added a pendulum.
Ah. What does the pendulum cause it to do?
The pendulum causes it to move. The pendulum moves at a different rate than the actual building. So it would cancel out the center of gravity, and it would just stay.
Okay. Nice. So what he was saying is that the earthquake, he's busy finishing his final building, so the earthquake moves and creates these type of waves. But his pendulum made these kind of waves, smaller waves, and once these waves came into contact with each other, it would kill the vibrations between the two. Yes.
Can it be more than 20 stories?
It can be more than 20 stories. Would you mind anyone at this table explaining to me? So on this building here, what? Oh, I thought you were making the pagoda things. Can anyone explain to me why pagodas, Japanese pagodas?
Because they were flexible.
They were flexible, but what else did they have?
And each floor was built differently. So So the center of so each floor would move separately.
What caused it to move separately? So how did we recreate this in
The
our
center
building?
of weight.
Okay. Do you have any pieces that aren't stuck together completely?
Well, this one, yeah.
Okay. What's different about this piece? Okay.
It's able to move.
It's able to move. So what happens when this piece slides?
It helps it move.
Okay. If this piece moves, what's happening with the building?
It counters it out, right?
Yes. So another way is that if the building pieces slide back and forth, that creates waves as well. So I'm going to resume this video back when we can do some tests, and then we can talk about why certain things are more why certain buildings are more earthquake resistant than others.